Okay, so 2 is an isotherm. Okay, number 3. Okay, number 3 looks like this. Okay, the best we can do is say, obviously it's not an isobaric, it's not isochloric, it's not isothermal. If it's anything, it would be adiabatic. Okay? Now, that's really not a hard and fast proof that this is the adiabatic process. It's the best we can do going about it by a pretty easy methodology. Okay? Number 4, the 4th process goes straight down. What's not changing? Volume. Isochoric. Okay. Those are the easy ones. Okay? E. In which process or processes does the gas do work? Okay? The gas is doing work as opposed to work being done on the gas. The gas does work anytime what happens to the volume? Be more specific than changes. It increases. Anytime your sample, if you have a balloon and that balloon gets bigger, it's pushing out on the air around it. It's doing work. Anytime there's an increase in volume, the gas is doing work. Okay? So look at the graph. Processes 1, 2, and 3 all get bigger. In each case, work is being done. Okay? F. In which process or processes is heat removed from the gas? Okay. This one's a little bit more complicated. Requires a little thought. Okay? So let's go through these one at a time. For process number 1. Okay? To get, guys, there is no, if you have to get at heat, the only way to get to heat is through the first law of thermodynamics. We don't have a separate formula for heat other than that. So delta U equals Q plus W. Think about the first process now. In the first process, has delta U gone up? Yes. How can you tell if delta U goes up? Delta U depends on temperature. Remember? It does depend on work. It does, of course. But it also equals 3/2 nRT. Or is that KT? KT, my bad. Okay? So here's the deal. If you look at this point right here, I guarantee you if I start drawing isotherms on this graph, we know this line's isotherm. That would be an isotherm of a higher temperature that would cut through that point. If it's at a higher temperature, that point's definitely at a higher temperature. Okay, tell me about the work. Is work being done on the gas or by the gas as we go from here to there? Work is being done by the gas. So here's the deal. U is going up. If work is being done by the gas, work has a positive or negative sign. If U goes up, work is negative, Q must be what? Positive. Positive. Okay? So number one does not have heat being removed from the gas. Heat's got to be added to the gas. Okay? Go to number 2. Tell me about the temperature at the end of cycle 2. Same. At the end of cycle 2, the temperature is the same. So delta U is 0. Work during process 2, positive or negative. Work is being done by the gas, which means the work on the system is negative. Q must be positive. Okay, if Q is positive, no energy is being removed from the gas. It's got to be added to it. Okay? Come down to number 3 right here. In number 3, this is an isotherm cutting right through there. Number 2 is an isotherm. We've already said that. Number 3 is at higher or lower temperature. It's at lower temperature. So for process number 3, internal energy is going down. Okay? Work, positive or negative?
Negative.
The work?
Negative.
Okay, it's the gas is getting bigger. Work is being done by the gas. Therefore, the work is negative. Okay? Q. Well, maybe Q is 0. Actually, it's got to be 0 if you said it's what?
Adiabatic.
Adiabatic. And don't even go any further there. Okay? That brings me to this process. Process 4. Process 4 occurs at a constant volume. If you have no change in volume, what's your work? 0. So work is 0. Do you have a change in internal energy? Is this ending point on a lower isotherm? Yes. It's on a lower isotherm. Internal energy is going down. Therefore, Q must be removed. Okay? So number 4, process 4 is the only process where heat was removed. Okay? G. Which one ends on a higher isotherm? Process 1. Process 1 starts on this isotherm, ends on this isotherm. Okay? It's the one that's going to have a higher root mean square speed at the end. Okay. What I need you to do on your practice test, just start working it. I'll tell you what number to stop with. Well, I'm going to give you guys about 20 minutes to work on this. More practice with the second law, with the first law, excuse me, and then we'll get into heat engine. Go ahead and get started. Heat only flows spontaneously from where? Hot to cold. Mechanical work must be done to get heat to flow from cold to hot. It's possible. You can, a refrigerator does exactly that. Okay, but you got to put work in to make it happen. Okay. Processes proceed spontaneously from a blank state to a blank state. From a organized to a disorganized. Organized to random, whatever you want to say. This is the same as saying that the entropy of the universe is increasing. That naturally occurring processes increase the disorder of the universe. Okay? You take any man-made structure and you do nothing to it, it will eventually fall down. Okay? To keep things organized requires an input of energy. Okay? Total change in entropy for any spontaneous process. Again, that question mark, the question mark S, that should be a delta. Delta S equals S final minus S initial. That S is the symbol for entropy. And entropy is calculated Q over T. That's how entropy is calculated. So delta S is always increasing. Okay, that brings us to heat engines. Okay? Okay, on your sheet, I have drawn a diagram of a heat engine. If you can remember this diagram, okay, you know just about everything you need to know about heat engines. Okay? A heat engine has a hot reservoir. Here is the engine. And you have a cold reservoir. The idea is heat flows from the hot reservoir. We call that QH. It goes into the engine. Part of that heat that goes in comes out in the form of work. That's why it's an engine. It does work. But not all of what you put in becomes work. Some of what you put in gets exhausted to the cold reservoir, QC. Now, if we just look at the picture, conservation of energy says that QH should equal the sum of what? W plus QC. What you put in has to equal what you get out. That's conservation of energy. Okay. In this topic, we also talk about efficiency. Efficiency. Symbolized by little e. Efficiency. Efficiency of anything is what you get out divided by what you get put in. What are you ideally getting out of a heat engine? Work. What are you putting in? Heat. Okay, so the efficiency is the work divided by QH. Okay? That is the efficiency of the heat engine. Now, sometimes you don't know what the work is. If we come right up to here, guys, and rearrange and solve for work, we get QH minus QC equals the work. If I drop this back down into here, I get the efficiency is QH minus QC over QH. And if I break this fraction apart a little bit, we get 1 minus QC over QH. Gives us another way to calculate efficiency. Okay? Now, there was a French guy named Carnot. Okay? And Carnot had invented this thing called a Carnot engine. A Carnot engine is an ideal engine. It doesn't really exist.
We didn't invent it. Made it up.
Okay. Now, this Carnot engine, this fictitious engine that doesn't really exist, okay, it has some important applications. Okay? The first thing you need to know about a Carnot engine is it is reversible. That is, if you have a Carnot engine, it would be possible to run this thing in reverse and put QH back in with no loss of energy. Okay? No naturally occurring process is reversible. So that's the first reason why a Carnot engine doesn't exist. Okay? Now, for a Carnot engine, we have an infinitely cold, we have a hot reservoir that's very, 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 very big. We have a cold reservoir that's very, 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 very big, such that their temperatures never change. So I have a TH up here, TC down here, and these remain constant. And again, for a Carnot engine, and for a Carnot engine only, the ratio of QC to QH is equal to the ratio of TC over TH. And herein implies the utility of the Carnot engine concept. Okay? Because heat flow is really difficult to measure. How do you go out and measure the amount of heat your car is dumping into the environment? I mean, some of that heat's coming out the exhaust pipe, some of it's radiating off the motor. How do you measure all that? Okay? What you can measure easily is what is the temperature of the environment? Take a thermometer. What is the temperature inside the motor? Again, insert a thermometer in the motor. Those are two things that are easy to measure. And by assuming it's a Carnot engine, what we can get is we can calculate an ideal efficiency. Because I can come right here, and again, only valid for a Carnot engine, I can replace QC. This should be QH down here. My bad. I can replace this ratio with 1 over TC minus 1 over TH. And that would be the efficiency of a Carnot engine. Okay? Now, guys, what is the only way you can have an engine that's, in terms of this formula, what is the only way you can have an engine that's 100% efficient? What does the temperature of the cold reservoir have to be?
0.
0. Absolute 0. That can't happen. Which means no engine whatsoever can be 100% efficient. It's impossible. If an ideal engine can't be 100% efficient, no real engine can.